Systecon are experts in producing world-leading logistics software. The tool suite includes OPUS10, a comprehensive and flexible model that enables the identification of maximum availability for minimal cost by recommending an optimum spares assortment, repair policy and support structure. It is now one of the world's most powerful logistics support optimization programs. This demonstration describes how a model is defined in OPUS10. OPUS10 allows the user to define their scenarios by breaking down the model into four main areas: the equipment breakdown structure, the logistics support organization, maintenance and storage capabilities, and model control. The user interface for building the problem has two views. Previous users of OPUS10 may feel more comfortable with the traditional table view for defining their model. But by selecting the item view, the modeler can easily keep track of their model as it is developed, allowing the analyst to easily visualize their equipment breakdown structure, logistics support organization, and other associated data. Let us look at a simple example and see how the data to define the model is entered. This example only considers the mandatory forms for a steady-state scenario, but it should be noted that other forms are available, either to activate other functionality of the tool or to refine the model description. For example, the analyst might wish to run an endurance-type problem, or specify how a system is repaired by declaring the replacement time for each of its LRUs, rather than specifying an overall system repair time. We'll start with the three control forms. First, the problem description. This is a free text form where the analyst can record details about the model. In addition, a notes field is included in virtually all other tables and allows the analyst to enter free text alongside each entry in a table. The control parameters form is used to specify limits to the model or switch specific features on or off. The global parameters form is used to specify such things as the interest rate for net present value calculations, or the default man-hour rate to be used throughout the model. To define the equipment breakdown, we start with the system table. Here, all system identifiers to be included in the model are defined. The identifiers may be for one or more end systems, or subsystems. If subsystems are to be considered, their relationship with the parent would be described in the system structure table. It is also possible to define base systems, from which other similar systems can be built. This is useful when several marks of a system are to be modelled and only some items within each mark differ. OPUS10 can handle any number of systems or system types, and is only limited by the capabilities of the host computer. The item table defines all unique items included in the model. Here, the item price and failure rate are detailed. Other data can also be specified, for example, the number of spares already in existence. The item structure details the item relationships within each of the other items or systems in the model. Items can belong to one or more parent items or systems. As with systems, there is no limit to the indenture levels in the equipment breakdown, and like items can be defined at different indenture levels if required. It is also possible to detail an environment factor to adjust the declared item failure rate for a specific installed location. Next, we move to the logistics support organization and start with the station form. Here, all the unique stations are declared together with their storage and repair capabilities. In addition, it is possible to assign stations to a lateral support group, allowing lateral supply to be carried out if required. The station structure form details how stations are related, how long it takes to carry out transfers between them, and if appropriate, how much it costs. This is effectively the default support organization, and if required, it can be overridden for specific items, groups of items, systems, or groups of systems. Once again, there is no limit to the number of echelons defined in the model. Next, we tie the systems to the stations by using the system deployment table. This describes how many of each system type are deployed and how much they are used. Now we come to the system and item recovery data. Starting with the system repair form, we can describe how the systems are repaired, how long it takes, and if appropriate, specify some costs, either in terms of man-hours and/or repair costs. This table can be overridden by using the item replacement table and defining data for specific items in their installed positions. Note also that systems do not have to be recovered at their operating sites. This covers situations where systems may be transferred to other locations for recovery. The item repair form describes how items are recovered, how long they take, and how much it costs. Again, either in terms of man-hours and/or repair costs. Like the system, the entries here can be overridden by more detailed information declared in the item replacement table. In situations where items are discarded, entries will be declared in the item reorder table. Sometimes it's necessary to restrict stock levels or set minimum values. This can be done by using the item station data table. Entries in this table override the station table for the items included in it. It is also important to note that input files are generated from templates. These can be user-defined. By creating templates, users can predefine their own set of forms, each with its own customized set of columns. For example, in some cases it is possible to adjust the default value, time period, or even the text. This is great for our customers whose first language is not English. Whilst being built, the model can be tested at any time. This will generate a comprehensive log window, which allows the user to quickly identify and track down problems with the defined data. This same test and log window are used when the model is executed. At any time during the development of a model, the user can use the built-in analysis tool. The analysis view allows the user to better understand their model and identify intermediate results such as repair actions or installed quantities. In addition, with only basic data entered, it is also possible to start identifying items that may be cost drivers, or view the item tree from the bottom up. It's important to note that this is merely an overview of the model, and many features have not been covered. For more information about our tools, please select another demonstration. Or for more detailed information about our products, please contact us or visit our website at www.systecon.co.uk.